Welcome to our Quantum Deep Dive.
Great to be here.
Today we're tackling a really core piece of the puzzle in quantum computing right now, the Variational Quantum Eigensolver. You'll often hear it called VQE.
Yeah, it's absolutely one of the main algorithms, kind of a workhorse for the quantum computers we actually have access to these days. It sort of bridges that gap between all the theoretical power and, practical application.
Exactly. And our guide for this particular deep dive is an insightful essay by Jorgo Schneepatt.
Mm-hmm.
So our mission today is really to unpack the crucial takeaways from his material, try and cut through some of the technical layers, understand what VQE really is, and critically why it should matter to you, the listener.
Right. Think of it as getting the essential knowledge on a key bit of quantum tech that could unlock solutions to problems that are just, currently out of reach.
Because VQE is a prime example, isn't it, of how we're starting to actually harness these weird quantum effects to tackle real challenges that just completely choke classical computers.
Yeah, it sets the stage for potentially powerful future applications.
Okay, so let's jump right in. At its heart, what is the Variational Quantum Eigensolver?
Fundamentally, VQE is a hybrid quantum classical algorithm.
Hybrid meaning?
Meaning it smartly combines the unique ability of quantum computers handling really complex quantum states with the well-established power of classical computers for optimization tasks.
Okay, right. So it leverages the best of both worlds, kind of. And what's its main job? What's it designed to do?
Its primary purpose, its main goal, is to find the ground state energy of a quantum system.
Ground state energy.
Yeah, this is super relevant in fields like chemistry. The ground state energy of a molecule, for instance, tells us a huge amount about its stability, its reactivity, its properties. It's basically the lowest possible energy configuration that system can settle into.
And finding that absolute lowest energy point, that gets incredibly difficult for classical computers as the systems get bigger.
Oh, absolutely. Precisely. The difficulty just explodes. Now, to really get how VQE works, we do need to quickly touch on some fundamental quantum ideas. The essay highlights these. Things like superposition.
Right, the idea that a quantum bit equibit can be both 0 and 1 at the same time. Sort of.
Exactly. That's the essence. You might see the math like CI alpha 0 plus beta 1, but the core idea is this simultaneous existence in multiple states.
And then there's entanglement, which is even weirder, where particles get linked and measuring one instantly affects the other no matter the distance. Like that Bell state example, 5 plus Frank 1 plus 11 wrangle.
Yep. Those properties, superposition and entanglement, that's where quantum computers get their potential power. But the real mathematical engine behind VQE is something called the variational principle. It's actually quite an elegant idea from quantum mechanics. It basically says that for any guess you make about the state of a quantum system, any trial state, the average energy you calculate for that guess state will always be higher than, or at best equal to, the true absolute minimum ground state energy.
Ah, okay. So you can never accidentally dip below the true minimum with a guess.
Exactly. So if you keep making better guesses for the state, maybe tweaking them somehow, and the average energy you measure keeps going down.
You know you're getting closer to the real thing, to that true ground state minimal.
Precisely. And that is exactly what VQE does. It uses this principle in like a loop, an iterative loop that involves both the quantum and the classical computer working together.
Okay, walk us through that loop. How do the two parts actually interact?
Right. So it starts on the quantum computer. It prepares a specific quantum state, which is often called the ansatz.
Ansatz. Fancy word.
Yeah. Think of the ansatz as like a template or a structured guess for the system's state. It's a mathematical description, a wave function, but it has adjustable knobs built in. Parameters, we often call them theta.
So the quantum computer sets up this specific state based on some initial settings for these adjustable knobs, these parameters.
Yes, exactly. This state is usually created using what's called a parameterized quantum circuit. Then the quantum computer measures the energy of this state.
How does it measure energy?
Well, it involves the system's Hamiltonian, that's the operator describing its total energy.
Yeah.
You translate that Hamiltonian into something the quantum computer can measure, often breaking it down into simpler bits called Pauli operators. Then you measure those and combine the results to get the expectation value, basically, the average energy of the state you prepared.
Got it. Quantum computer prepares a state, measures its average energy. Then what?
Then that energy measurement gets passed over to a classical computer.
The regular computer.
Right. The classical computer takes that energy value and uses standard optimization algorithms, things like gradient descent or maybe more specialized quantum-aware ones, to analyze it. Based on that energy, it calculates how to tweak those parameters, those theta knobs.
To hopefully get a lower energy next time.
Exactly. It's trying to find the direction downhill, so to speak, in the energy landscape.
And then the loop repeats.
Precisely. The newly adjusted parameters are sent back to the quantum computer. It prepares a new ansatz state with these updated settings, measures the energy again, passes it to the classical computer, which refines the parameters further.
You keep going round and round.
You keep going until the measured energy kind of settles down, until it stops dropping significantly. That signals you've likely found the best approximation of the ground state energy that you can get with that particular ansatz and your optimization method.
Okay, this brings us to a really crucial point then. If classical computers are so good at optimization, why do we even need VQE? Why can't the classical computers just find this ground state energy on their own?
That comes back to the fundamental scaling problem. The limitation of classical computers when you're dealing with quantum systems. As the essay points out, the sheer number of possible states a quantum system with n particles, say n qubits, can be in. It grows exponentially, like O to n.
Exponentially. That's the killer word, isn't it? It just balloons incredibly fast.
It really does. Even for fairly small molecules, trying to accurately describe or store this huge state space needs an amount of classical memory and processing power that just rapidly exceeds anything we have, or frankly can even imagine building.
So classical methods have to cheat somehow.
Well, they use approximations. Methods like Hartree-Fock or DFT, density functional theory, are widely used and very useful, but they have inherent approximations that limit their accuracy, especially for really complex, strongly correlated systems where quantum effects are dominant.
Right, but then our current quantum computers aren't exactly perfect, error-free machines either, are they? We keep hearing about this NISQ era, noisy intermediate scale quantum.
That's a critical piece of the puzzle. Today's quantum computers are indeed noisy. They're susceptible to environmental interference, they lose their delicate quantum properties, their coherence relatively quickly. And the operations, the gates, aren't perfect. They introduce errors.
So they can't run super long, perfect calculations yet.
Not without extensive error correction, which requires vastly more and better quality qubits than we currently have. That's still a major development effort.
So VQE is basically designed to be useful, despite these noisy, limited quantum computers we have now.
Exactly. That's one of its key strengths. By offloading the really heavy lifting of the optimization search to the classical computer.
Which is good at that part.
Right. And only asking the quantum computer to do relatively short, specific tasks, prepare a certain state, measure its energy, VQE, is designed to work within the constraints of NISQ hardware. It tries to minimize the depth of the quantum circuits needed.
So it uses the quantum computer for the part that's classically hard managing those complex quantum states, and the classical part for the optimization.
That's the core idea, playing to the strengths of each. But actually implementing VQE, it's definitely not smooth sailing. There are significant challenges.
We mentioned noise already, right? That's got to be a big one.
Oh, it's huge. Noise and decoherence. Any errors that creep into the quantum computation directly mess up the energy measurement you get out.
Which means the classical optimizer gets bad information to work with.
Exactly. Garbage in, garbage out, potentially. Now, there are techniques people are developing called error mitigation strategies. Things like zero noise extrapolation, where you try to estimate what the result would be without noise by running experiments at different noise levels. But they're not perfect cures.
And the optimization itself can run into trouble, even on the classical side.
Absolutely. The sort of energy landscape that the classical optimizer is exploring can be really complex. Think of it like a hilly terrain. The optimizer can easily get stuck in a small dip, a local minimum.
Which looks like the lowest point nearby, but it's not the lowest point overall, the true ground state.
Precisely. Finding that true global minimum can be very hard.
And the essay also mentions something called barren plateaus. That sounds bad.
Yeah, that's a particularly tricky one, especially as you try to scale VQE up to larger problems. In the very high dimensional space of all those parameters, theta, the optimizer is adjusting, the landscape can become incredibly flat. Just vast, flat plains. Meaning the gradient, the signal that tells the optimizer which way is downhill towards lower energy, becomes vanishingly small almost everywhere.
So the optimizer just gets lost. Doesn't know which way to go.
Pretty much. It effectively grinds to a halt, progress becomes incredibly slow or stops altogether. This seems to be a fundamental issue linked to the structure of many common ansatz circuits, especially as the number of qubits grows. It's a major research challenge.
Okay, so we get what it is, and we see the hurdles.
Huh.
But despite all those challenges, where is VQE actually starting to show some real promise, like real-world potential?
Well, one of the most immediate and I think significant areas is definitely quantum chemistry, simulating molecules.
Because that's exactly the kind of problem where classical computers hit that exponential wall we talked about.
Exactly. And finding that ground state energy is so key for chemists.
Right, you said it tells them about stability, reactivity.
Yeah, it lets you calculate fundamental properties, bond links, how reactions might proceed, how the molecule interacts with light spectroscopic data. The essay gives the standard examples, starting small, like hydrogen, H2, or lithium hydride, LiH.
The simple test cases.
Right, the early benchmarks to just show, okay, this VQE concept can actually work and give results that match known values.
But the real prize is bigger stuff, right?
Oh, yeah. The real target is simulating much larger, more complex systems that are currently just intractable classically. The essay specifically points to FOMOCO.
FOMOCO.
Yeah, it's the iron molybdenum cofactor. It's the active site in the nitrogenase enzyme.
Which stuff?
It's responsible for biological nitrogen fixation, taking nitrogen from the air and converting it into ammonia, which plants can use. It's a hugely important process for life and for agriculture, but it's incredibly complex chemically.
And simulating that accurately could give huge insights.
Potentially profound insights, yeah. Understanding exactly how it works at the quantum level could maybe lead to better artificial catalysts for making fertilizer, for example.
Wow, okay. So, beyond chemistry, what other fields are looking hard at VQE?
Material science is another major one. Very similar underlying problem, understanding the electronic structure of materials.
To design new ones.
Exactly. To design materials with specific desired properties from the ground up. Think about developing, say, high-temperature superconductors or more efficient materials for solar cells, photovoltaics, or designing better catalysts for industrial chemical processes.
So it's like molecular engineering, but for solid materials too.
You could think of it that way, yeah. Tailoring materials based on predicting their quantum behavior. And VQE isn't just limited to simulating physical systems like molecules or materials. It can actually be adapted for complex optimization problems.
Optimization. Like finding the best solution among many possibilities.
Exactly. Problems you find all over the place. In logistics, finance, operations research.
How does that work?
Yeah.
How do you optimize with VQE?
Well, the trick is to map the optimization problem onto a form that looks like finding the ground state of some artificial quantum system. You construct a Hamiltonian whose ground state encodes the optimal solution to your problem.
Huh. That sounds clever, but maybe complicated.
It can be, yeah. Designing that mapping is key. But if you can do it, VQE can then be used to find approximate solutions, often very good ones, to these optimization challenges. The classic example that always comes up is the traveling salesman problem.
Right, finding the shortest route to visit a bunch of cities.
Yep. That's a notoriously hard optimization problem, classically.
Okay, so connecting this back to industries, where might we see the impact?
The potential is really widespread. In pharmaceuticals, like we touched on, more accurate molecular simulations could dramatically speed up drug discovery, help understand protein folding, which is linked to diseases.
Big potential there.
Huge. In logistics, maybe optimizing complex supply chains much more effectively than we can now. In finance, maybe finding better strategies for managing investment portfolios, assessing risk. Basically, anywhere that classical methods are really struggling with that exponential complexity, VQE offers a potential way forward, even with the NISQ machines we have today. Looking ahead, the future potential of VQE really hinges on progress in, I'd say, two main areas: hardware and software.
Better quantum computers and smarter algorithms to run on them.
Pretty much, yeah. On the hardware side, as quantum computers improve, getting more qubits, sure, but crucially, lower error rates and longer coherence times.
So you can run deeper circuits more reliably.
Exactly. Then VQE simulations will naturally become more accurate, and we'll be able to apply them to larger, more complex problems that are out of reach today.
And what about the software side? The algorithms?
Well, that means developing better classical optimization techniques, ones that are more robust to the noise coming from the quantum computer and better at actually finding that global minimum, avoiding those local traps and navigating those barren plateaus we talked about.
Right.
It also involves designing better ansat states, finding that sweet spot where they're expressive enough to actually capture the true ground state physics, but also simple enough or structured enough to be trainable and runnable on NISQ hardware without hitting those plateaus too quickly.
And the essay also mentioned possibly integrating VQE with AI, machine learning.
Yeah, that's a really exciting and active area of research. ML could potentially help in several ways, maybe using machine learning to help select or even automatically design better ansat structures for specific problems.
So AI helps build a quantum program.
Could be. Or using ML to optimize the parameters theta more efficiently, maybe learning from previous runs, or even using it to help mitigate or correct for the errors in the quantum measurements themselves. It's all about building even smarter, more sophisticated hybrid approaches.
Okay, so let's try and sum up this deep dive then, drawing from Jorgo Schneppe's essay on VQE.
Right. It's clearly a vital algorithm. You could say it's a cornerstone for this current era of quantum computing, the NISQ era. It's fundamentally hybrid,
Combining that quantum state preparation and measurement part.
with classical optimization muscle.
And its main job, its core task, is finding that ground state energy, especially for systems like molecules or materials that are just too complex for classical computers.
Which potentially paves the way for breakthroughs in chemistry, material science, maybe even optimization problems in other fields.
And while it definitely faces big challenges, noise, those tricky optimization landscapes, barren plateaus.
Yeah, those are real hurdles, but the key is that VQE is designed to try and function, despite those limitations, on the noisy hardware we have right now.
So it really acts as a crucial bridge, doesn't it? Connecting today's capabilities to future, hopefully more powerful, fault-tolerant quantum computing.
I think that's a great way to put it. It highlights how we're figuring out how to build practical tools with the quantum technology we actually possess today. Even if it's not perfect yet, it's a stepping stone.
Okay, before we wrap up, drawing inspiration from the source, here's maybe a final thought for you, our listener, to mull over. Given this ongoing, rapid but maybe uneven progress in quantum hardware and all the work going into better algorithms and error mitigation, how do you think the practical capabilities of VQE simulations might evolve in the very near term, say the next 3 to 5 years? And maybe more pointedly, what do you think are the most likely first real-world applications that will actually move beyond just academic research papers and start making a tangible impact? Thank you for joining us for this deep dive. Goodbye.
Goodbye.